Alright, so we're going to get started in Chapter 4, and Chapter 4 has a bunch of definitions, so we're going to start off defining quite a few different things. So let's take a look. So the goal of Chapter 4, Section 1 is we want to talk about maximum and minimum values. So some of the most important applications of differential calculus are called optimization problems, in which we are required to find the optimal way of doing something. So we'll get to do some of these things. So, for example, what is the shape of a can that minimizes manufacturing costs? What's the maximum acceleration of a space shuttle? What is the radius of a contracted windpipe that expels air most rapidly during a cough? And at what angle should blood vessels branch as to minimize the energy expended when pumping blood? One thing we will discover about nature is very efficient. It will always find the lowest energy way to do things. So when we do some of these optimization problems, we'll help discover some of those things. So basically, the goal, at least for the first part of Chapter 4, is this idea of finding maximums and minimums. So we're going to have a couple of different definitions and then different ways to find them. So let C be a number in the domain D of a function, then f of C is the absolute maximum of f on D if f of C is bigger than f of x, greater than or equal to, actually, for all x in D. So notice, we do have that greater than or equal to. So as much as the name makes it sound like there can be only one, it is possible for a function to have more than one absolute max, but they would have to have the exact same value, just be located at different places. Similarly, we have the negation, or the opposite of that, which is if C is a number in the domain of the function D, or in the domain D of a function f, then f of C is an absolute minimum for f on D if f of C is less than f of x less than or equal to for all x. So in terms of what we've seen, we're used to seeing maxes and mins like this, where maxes and mins occur at places where our graph changes from increasing and decreasing, and from decreasing to increasing. Turns out that's not quite the whole picture, so we'll keep expanding on this. So the key idea here that we're going to expand some of these things to is going to be global means it's true for everything. Now we want to talk about a more local concept. So if we take this same idea, we're going to look at another picture to help us expand on some of these definitions. So we want to talk about local maxes and local mins. So f of C is a local maximum value of f if f of C is greater than or equal to f of x for all x near C. So let's quantify what that means. So when we say near C, what we formally mean is for any open set centered at C, for every x in the open set, x not equal to C, we have that f of C Oh, sorry, I'm getting for when we so essentially what we're saying is that if we take some small number centered at some point, so let's go here, so centered at E, so imagine if we had E minus H and E plus H. That would be an open set around the point E for H small. And so what we're saying in this definition is that f of c is a local maximum or a local min if we can make an open set around a point where that center point is either the greatest value or the smallest output for the function. So the set can be infinitesimal. So that's why we make it a local phenomenon. So an open set around a point is really just a teeny tiny little neighborhood around that point for any small number h, so like 0.00000001, as long as you can create a small neighborhood around that point where it is either f of c is either the biggest or smallest value, then we have a local max or a local min. Global, as we saw in the previous, means for all x in the domain of the function. So in terms of this picture then, we could create open sets around almost all of these points. So here we would have a local max. Here we would have a local max. And here we would have a local min. Because in some small neighborhood around those points, they are either the highest point or the lowest point. Not universally, but in some small neighborhood. So then, we weren't asked this, but in this picture, where would our global or absolute maximum be? At D. And where would our global or absolute minimum be? Are we sure about that? What about A over here? Right? So this would be our global min. Our global max would be the same as that. And we'll notice a couple of things. Our graph at this point right here does change from decreasing to increasing, but it's at a cusp. So our function would not have a derivative at that point. So we're going to need more analysis than just the derivative, which is pretty much what we've been using before when we were talking about finding maxes and mins, because we were just talking about slopes. But at that point, our slope doesn't exist. So let's keep that in mind as we move forward. All right, so let's take a look at a couple of examples to go with these definitions. So example 1, the function f of x equals sine x takes on its local and absolute maximum value of 1 infinitely many times, right? Because our sine wave goes up, comes back down, goes back up, and it does it forever in both directions. So we have our maxes, we have our mins, and they are both local and global because they are all equal to the same value of 1. Right? All right. Let's take a look at our next example. So example number 2 is if we look at the parabola f of x equals negative x squared, this has a local and global maximum right here at the point 0, 0. So this is local and global. But this has no minimums, right? Because our graph continues on forever in both directions. So it does not have any local or global minimums because it goes to negative infinity. So our first example had an infinite number of maxes and mins, and they were both local and global. In this one, we had only local and global maximums and no minimums, and they happened to be the same point. So then, if we take a look at example number 3, we now have our cubic function, and when we look at the graph of this picture, or the picture of this graph, does it have any local maxes or local mins? And the answer is no. And it has no absolute maximums or absolute mins, right? It goes forever in both directions. Even more so, if we take its derivative, what is f prime of x? We get 3x squared, right? So then if we set f prime of x equal to 0, that gives us 3x squared is equal to 0. We divide by 3, divide by 3. So we get x squared is equal to 0. Taking our square root, we get x is 0. So when x is 0, what's our slope? 0, right? Do we have a max or a min there? No. So in this case, once again, our function has a derivative. Its slope is 0, but what happened? It was going up, it briefly stopped, but instead of going back down, what happened? It kept going up. So does it have a max or a min there? No. So once again, the derivative didn't give us the whole story in this case. So we're going to have to be a little bit careful. So this has no maxes and no mins. All right, so the next one is for you guys, and it says, find the local and global maximums of cosine. All right, so let's find all of our local and global maximums. So if we were to graph our cosine function, on the standard 10 by 10 window, we get something that looks like this. And similar to the sine function, since it's a wave, it's going to achieve its global maxes and mins and local maxes and mins an infinite number of times. So based on this picture, we're going to have our global max here and local. And we're going to have our global and local min. So we know we can find these by setting it equal to those values. So cosine x, we want to know, well, when does it equal to 1? So we take the inverse cosine of both sides, and we get the inverse cosine of 1, which is going to be, as we see from our graph, 0. But then it happens every 2 pi units, so plus 2 pi n, where n is any integer. We're going to get something similar when we do it for minus 1. So the cosine of x is equal to negative 1. We take our inverse cosine of both sides, and we're going to get x equals, the inverse cosine of negative 1 happens at pi, and it's also going to be 2 pi periodic. So 2 pi n for our n being any integer. And that would get us all possible solutions. All right, so our next theorem tells us the following. So we saw in some previous examples that not all functions, so therefore their graphs, will have global maxes or mins. The extreme value theorem gives us the conditions which guarantee that a function will have an extreme value. So the two things that have to be true is f has to be continuous, and it must be continuous on a closed interval. So if f is continuous on a closed interval, then f attains an absolute maximum value and an absolute minimum value for some numbers c and d in that closed interval. And in case you're not familiar, this symbol here is our set symbol for in, or element of. So this basically tells us that if f is continuous on a closed interval, we are guaranteed to have a maximum value and we are guaranteed to have a minimum value, both of them absolute. All right, so before we actually use this, let's see that each of those two conditions that were highlighted are necessary. So the domain being closed is necessary. So if we have f of x equals 1 divided by x minus 1 on the domain 1 to positive infinity, this is open, not closed. So closed sets include their endpoints. So in this, we don't include 1, and we can never include infinity because infinity is not a number, right? And on this domain, since our domain's not closed, this function does not have an absolute value or an absolute maximum. It goes up forever and ever and ever, so it goes all the way up to positive infinity, and it goes down forever and ever, but it never actually reaches 0, right? So it has neither an absolute maximum or an absolute minimum. All right. Our next one is that being continuous is also a necessary condition. So if f of x isn't continuous, all sorts of weird things can happen, right? So if we had a function that looked like this, it's not going to have an absolute maximum, right? Because it never actually makes it to this point because it's open. So this graph would not have an absolute maximum. So if a function is not continuous, then we are not guaranteed to have absolute maxes and mins. So for the extreme value theorem to apply, the function f must be continuous, and the domain in question must be a closed interval. If that is the case, then f obtains an absolute maximum and an absolute minimum on that interval. So to make matters even worse, these conditions are necessary, but not sufficient. So you can have graphs that will have absolute maxes and mins that don't fit that criterion. But this is the set that guarantees that that will happen. So if this then we get the conclusion, but there may be functions that don't satisfy this that still have absolute maxes and mins, right? So just because something doesn't satisfy this, it doesn't mean that it doesn't have an absolute max or an absolute min. So we have to be a little careful with the logic there. All right, let's take a look at our next example. Oh, sorry, I'm a liar. We're going to look at a theorem. So we've been dancing around this, and Fermat's theorem quantifies what we've been hinting at so far. So it says if f of x has a local maximum or local minimum at C, and if f prime of C exists, then f prime of C is equal to 0. So when we look at this, it's not quite what we want, which would be if f prime of C equals 0, then we have a local max or a local min. But we know that statement's not true. This says if it has a local max or a local min, and if f prime of C exists, then f prime of C is equal to 0. So the proof is basically using the difference quotient from the left and from the right. If we take the left limit and the right limit, as long as f is continuous, we will get that the limit from the right of f prime of C is less than 0, and the limit from the left would be greater than or equal to 0. So then by the squeeze theorem, if something's greater than or equal to 0 but less than or equal to 0, then it must be 0. So this basically confirms that not all extreme values can be found by setting f prime of x equal to 0. It's not to say that that's not going to be part of our tool set. In fact, it's going to be one of the main parts of things we're going to do, but just be aware that it is limited. It is not the only place where this can happen. All right, so we actually already did example 6, but we'll talk about it again, and we'll focus then on example 7. So as we saw earlier when we looked at the graph of f of x equals x cubed, and when we set its derivative equal to 0, f prime of 0 is 0, but as we saw above, the function doesn't have any extreme values. So we had a derivative equal to 0, but we did not have a max or a min value there. All right, the function f of x equals the negative absolute value of x minus 2 plus 1 has its local and absolute max at x equals 2, but the function is not differentiable there. So if we were to graph f of x, so our parent function would be the absolute value of x, right? And we know that the generic absolute value function looks something like this, right? So then this is going to be a reflection the minus 2 is going to shift right 2 units, and the plus 1 is going to make it go up 1 unit. So if we do those things, we flip it over, we go right 2, and we go up 1, we're going to get a graph that looks something like this, right? Oh, so just as advertised, we indeed do have both a local and global max. So what is the slope at that point? Well, to the left, we have a straight line segment, and its slope's going to be positive 1. And to the right of it, what's its slope going to be? On this branch right here, it's going to be negative 1. So how do we differentiate an absolute value? So that's something we really talked about. But if we go back in our time machine, we have the absolute value of x is the same as the square root of x squared, right? We used that earlier when we were calculating limits. Well, we know how to take the derivative of this. It would be the chain rule, right? So if we have f of x is equal to x squared raised to the 1/2 power, we would have that f of u equals u to the 1/2, and u is equal to x squared. So then our derivative, f prime of x, is equal to df du times du dx. So we get 1/2 u to the negative 1/2 times du dx, which is 2x. Our 1/2 and our 2 reduce out. And then we're left with x over u to the negative 1/2 goes to the square root of u. So then finally we substitute that out. U is x squared, so we get x over the square root of x squared. But the square root of x squared is the absolute value of x. So what does that function look like? Well, if x is negative, what are we going to get? Well, if x is less than 0, we would have x over negative x. And if x is greater than or equal to 0, nope, greater than 0, not equal to, greater than 0, we would have x over x. And if x equals 0, what do we get? Undefined, right? Because you can't divide by 0. So then, what's x divided by negative x? Negative 1. What's x divided by x? 1. So if you draw a graph of the derivative of the absolute value function, it looks like this. Does that make sense? Yeah, because when we look at our thing up here, what's our slope until we get to our vertex? 1. And what's our slope here? We did the generic function instead of the actual one that we had, but the process is exactly the same. So it turns out in this case that our function has both a local and global max, but the derivative wasn't 0, but what was it? Undefined, right? So turns out that's going to be important. So that gives us our next definition. So definition of a critical number. A critical number of a function f is a number c, and what has to be true about it? It needs to be in the domain of f, and then we have an or statement. It either f prime of c has to be 0 or f prime of c does not exist. So to be a critical number, it has to be in the domain of the function f, or we don't care about it, and it has to be either f prime of that number is 0 or the derivative of that does not exist. All right, let's go ahead and do an example. So we want to find the critical numbers of this. So what rule are we going to use to find our critical numbers? We could use the product rule, or we can just distribute, right? And then just use the power rule. So we'd have 4x to the 3/5 minus 1 plus 3/5 is x to the 8/5, right? So then we take our derivative. So f prime of x is equal to 4, and then we have 3/5 comes down in front. X, 3/5 take away 1. Well, 1 is the same as 5/5. So 3/5 take away 5/5 is negative 2/5 minus 8/5. And then we have x. 8/5 take away 5/5 is 3/5. So that gives us 12 over 5x to the 2/5 take away 8x to the 3/5 over 5. So now we need a common denominator. So I multiply the top and the bottom by x to the 2/5, and that gives me a common denominator. So then I have 12 minus 8 x to the 3/5 times x to the 2/5. We add our exponents. So 3/5 plus 2/5 is 5/5, which is 1, so just x, over 5x to the 2/5. So now, by definition, our critical numbers are when it's equal to 0 or when it is undefined. So to find when it's equal to 0, we need to solve 12 minus 8x equals 0. Or when it's undefined, we set the denominator equal to 0. So 5x to the 2/5 is equal to 0. So solving our first one, we add 8x, we add 8x. And this gives us 12 equals 8x. We divide by 8, we divide by 8, and we get x to the, each of them are divisible by 4, so we get 3/2. Or this one, well, two things when they multiply together equal 0 if and only if one of them is 0, so that's when x equals to 0. So now we need to check, are these in the domain of the function? And the answer is yes, the domain of this function is all real numbers. So both of these are our critical numbers. So our critical numbers occur at 3/2 and at x equals to 0. All right, let's graph this thing and see what it looks like on our calculator. So if we go x raised to the 3/5 and we multiply it by 4 take away x and we graph, we get something that looks like this. So let's zoom in a bit. So zoom in, press enter. I went down too far. So let's make our y-max a little bit bigger. And there we go. So it appears we're going to have a maximum at 3/2, but at x equals 0, something else entirely happens, right? But in both cases, this is a critical number of our function. All right, it's now your turn. All right, so let's go ahead and find the critical numbers of f. So we take our derivative. F prime is going to be 4t cubed plus 3t squared minus 10t. And polynomials are defined everywhere, so it's never going to be undefined, so we just need to solve then. F prime of t is equal to 0. So we have 4t cubed plus 3t squared minus 10t is equal to 0. we have a GCF of t in each of them, so we factor out our t, and that gives us 4t squared plus 3t minus 10 is equal to 0. So now we need to factor this quadratic trinomial, or just use the quadratic formula. So turns out that one's a little bit of a pain to factor. So we have t equals 0, or 4t squared plus 3t minus 10 equals 0. And we can just use the quadratic formula to find our solutions. So I'm going to just save these as a, b, and c in my calculator. So a is 4, b is 3, and negative 10 is c. And then alpha y equals, I have negative b plus the square root of b squared, take away 4 times a times c, all over 2a. And I hit enter, and I get 5/4, and then I press second enter to pull up what I typed on the previous line, and just go back and edit it, and change my plus to a minus, and hit enter. So then that gives me my two other critical numbers, which are 5/4 and negative 2. It does factor. You can use the AC method or guess and check, and if you factor it, you get the same solutions, right? It's just if I look at something and I don't immediately see how to factor it, when it's quadratic, you always have the quadratic formula as a fallback. So then those give us our critical numbers for this. All right, the next thing is, well then, how do we find absolute maxes and absolute mins? Well, we have a technique or a process or an algorithm, whatever you want to call it, to find absolute maxes and absolute mins if we have a continuous function on a closed interval. Because we know if we have a continuous function on a closed interval, they're guaranteed to exist. So this algorithm will find them 100% of the time. So we need to find the values of f at the critical numbers of f in AB, find the values of f at the endpoints of the interval, and then the largest of the values from the steps above is the absolute max, and the smallest of the values is the absolute min. So essentially, what this technique or this algorithm is telling us is that the absolute maximum and minimum of a function will either occur at a critical point or at the endpoints of the interval. So we find all of our critical numbers, then we test our function at all of the critical numbers and at the endpoints, and then we just select the largest and smallest values. And that gives us our absolute maxes and mins. Okay, so let's go ahead and do an example using this. So we wish to find the absolute maximum of f of x equals x minus 2 cosine x on negative pi to pi. All right, so first thing we need to do is find the critical numbers. So we set f prime of x, well, we find it, so the derivative of x is 1 minus 2, and the derivative of cosine is negative sine. So then that gives us 1 plus 2 sine x. So then we set that equal to 0 and solve. So we have 1 plus 2 sine x is equal to 0. We minus 1, we minus 1, And we get 2 sine x equals negative 1. Divide by 2, divide by 2. So sine x equals to negative 1/2. So then x is the inverse sine of negative 1/2. Okay, so then we need to find these values. So the first thing, the inverse sine will only give us values in what range? So it goes from negative pi over 2 to positive pi over 2. But we're concerned about negative pi to pi. So we're going to have to be a little bit careful. So if we think about sine, by definition, what is sine? Sine is the y value on our unit circle, right? So y is negative in quadrants 3 and 4. So sine then is opposite over hypotenuse. So we're going to have negative 1 and 2 and negative 1 and 2. So this is going to be a 1, 2 square root of 3 triangle, which then means each of these are going to be, our reference angle is going to be pi over 6. But we have to be careful because our inverse sine has range negative pi over 2 to pi over 2, right? So then if we're going to negative pi over 2 to positive pi over 2, that means this is, our reference angle is pi over 6. So this angle right here is actually going to be in this range is negative pi over 6. We also get one angle that is not in that range, which is here. And so this angle as measured from the x-axis is going to be negative 5 pi over 6. There are going to be solutions, some other solutions that we need to check, because what is the period of the sine function? Well, it's 2 pi. So if we add 2 pi to either of these, it's going to push us out of this range. So these are going to be our two critical values. And then we have our endpoints. So we need to check we have negative pi, positive pi, negative 5 pi over 6, and negative pi over 6. And these are the set of values we're going to check to see which is the maximum and which is the minimum. So we go back to our original function, not the derivative. So we're going to be checking in our original function, which is x minus 2 times the cosine of x. And we put that into our calculator, and then I'm just going to put in each of these numbers as we go. So we have negative pi. It gives us this alpha trace, and then we're going to do the same thing with positive pi. And then we need to check our other two values. have negative 5 pi over 6 and negative pi over 6. So we look at our list of numbers that we have, and we're going to select our largest and our smallest value. So it looks like this is going to be the absolute max. Is at x equals pi, and then we select our smallest value, which is going to be this one, and our absolute min is going to be at x equals negative pi over 6. And that would be the location of the absolute max and absolute min of that function. So let's go ahead and do try number 3. So we take our derivative, and f prime is going to be the derivative of x is 1 minus 2, and the derivative of the inverse tangent is 1 over x squared plus 1. So we get 1 minus 2 over x squared plus 1. So we set that equal to 0. So 1 minus 2 over x squared plus 1 equals 0. We add 2 over x squared plus 1 to both sides, and we get 1 equals 2 over x squared plus 1. We clear our fractions by multiplying by the LCD, which is x squared plus 1. They reduce out. And that gives us x squared plus 1 is equal to 2. So then we minus 2 minus 2. X squared minus 1 equals 0. Factor into x minus 1 times x plus 1. And we get the two solutions, x equals 1 or x equals 2, negative 1. We go back and we look at our domain. Our domain is the set 0 to 4. So we don't need to worry about this guy. He's not in the domain. So we reject that one. And then we test our critical number and our endpoints. So we're going to test 0, 1, and 4. So we grab our calculator, put in our original function, so y equals was x minus 2 times the inverse tangent of x. And we go alpha trace of 0, y1 of 1, and y1 of 4. So then we get the following values. And it looks like we're going to have our max at 4. And we're going to have our min at 1. All right. So that would be our absolute max and our absolute min of that function on the following set.